So that instrument will continue in the afternoon, and in the meantime, the topic suggested for the second part of my talk is clouds and climate. Is anyone who has not seen a cloud? Every one of us is. Okay. They are there quite often, especially in Bangalore. Almost 90% of the time you see them, some time of the day, not throughout the day. And they are there all the time, but what real role do they play in the Earth's atmosphere? When you see that, most of the time, practically they are doing nothing, just sitting there. Except one important thing, that's interacting and interfering the way the radiation interacts with the Earth's surface. Okay. They are very good scatterers and also absorbers of radiation. Okay, both way they do that. So therefore, one is like a particle, like any other aerosol. It is there in the sky, which interferes with the radiation component. Okay, that is one aspect. There is another aspect, which is they cause rain. Okay, when rain occurs, water vapor condenses, liquid is formed, right? So whenever vapor condenses into liquid, what happens? Heat is released. Okay, and when heat is released, that air becomes warm and slightly expands. Because of that, the buoyancy changes, so it generates a lot of vertical velocity. Okay, as a result, it leads to dynamic effects. Okay. So therefore, clouds are important as they interact with radiation, but otherwise they are passive dynamically, not much important. On the other hand, when substantial amount of water condenses and latent heat is released in a small place, then that changes the buoyancy locally and it leads to large vertical accelerations, change in the pressure, and leads to large-scale circulation. Okay, that's the dynamic effect. And many times, these two are combined. Okay, and therefore, one of the most critical components of Earth system is clouds. They have large influence on the climate. Okay, they can cause cooling as well as warming. It depends on where they occur, at what height, how much liquid water is there, in what form. All that matters. So, in fact, the details involved are so many that if you ask the question, do clouds cause warming or cooling? The answer is maybe, because it depends on so many other factors. They may be cooling as well as warming. Just to get you a feeling of where are the clouds, where they occur. Okay. So what is done is that if you go to one of these websites which give satellite data, like for example, you have this Dundee website which provides the satellite images around the globe. You can, incidentally, have you heard of INSAT 3D satellite? Okay, newly launched. What is special about it? It is a geostationary satellite. All INSAT series are geostationary, but this is the only satellite, geostationary satellite, that has a sounder. Okay, no other geostationary satellites have sounders. Okay, this is unique about it. So you get temperature and humidity profiles from INSAT 3D. Its data is available now. I am saying IMD website, and it is from this. Can you make out it barely, right? Wherever you see this white patch, the clouds are there. Okay. This is the infrared radiation, the radiation which is emitted by the Earth, from the Earth, and this is in the visible. It is the radiation which is scattered, solar radiation which is scattered back to space. Okay, these two are different. This is the emitted by the Earth. This is scattered back by the Earth. Okay, so what you see here is early around 8 o'clock in the morning. So part of the hemisphere is dark. The darkness is because it is not at morning there, still night. Okay. On the other hand, in the infrared, if you see, day and night makes no difference. You can see that where the clouds are. Okay, infrared is more of it. So when you see these clouds are there almost everywhere. Whether you take tropics, mid latitudes, or Antarctica or Arctic, everywhere clouds are there. Okay. At any given time, about 50% of the sky is cloud covered. Only question is the type is different. Height at which they occur, the shape in which they occur, all those things are different. Okay? But if you are a visitor from outside the earth and look at the earth, you see white patches covering 50% of the earth. Those white patches are nothing but clouds. Okay? So now you can imagine if clouds are occupying 50% of the earth, how much influence they have on climate. Mostly on, okay? They strongly interfere. So a couple of percentage, 2% change in cloud cover can offset your global warming. Okay? On the other hand, 2% decrease can lead to runaway green or global warming. Okay? It has very strong influence on the climate. So if I look at the clouds, they are there almost everywhere. And 50% of the sky is cloud covered at any instant. It is only spatial and temporal distribution changes. They appear in different sizes and shapes. Okay? And they occur at different heights, low level, mid level, high level. We'll see some sample of them. And one of the major tasks is vertical transport of water. Okay? Whenever you see the large cumulonimbus clouds forming, they take water vapor in the boundary layer or near the surface and redistribute in the vertical. Okay, that's what they do. So clouds are involved in the vertical mixing in the atmosphere. They also transport all the pollutants you release near the ground. Okay, and many times you see the cloud, it doesn't rain. Okay, so all clouds they don't rain. In fact, I should say most clouds don't rain. Only a small fraction, only 5% of the total 50% of the cloud cover you see, they are raining. Remaining 45% they are non-raining clouds. And they intercept short wave as well as long wave radiation, but differently. Now, in this short period I have, I'm broadly quickly going to cover some of these questions, like what is a cloud, what are the different cloud types, how a cloud forms, and then role of clouds in Earth's climate and clouds in a warmer globe. What happens when the climate changes? That part is speculative. Definition. In fact, cloud is a mixture. Okay? And it is a mixture of dry air, which is more than 97%. So more than 97% of a cloud is nothing but air itself, dry air. Then a small part of it is water vapor and condensed water. It could be in a liquid form or ice form or sometimes mixture of both. Okay, and that again is 0 to 2.5%. This is whether you measure by volume or weight makes no difference. If you measure by volume also, because water vapor once it occupies the full volume, right? So therefore, all this percentage is by weight. Okay, by weight, very small weight. Even the thunderstorm, which gives a lot of rain, if you actually look at the amount of water that is there, less than 2.5%. Okay, more than 97% is still only dry air. What about the size? It could be as small as few tens of meters. Okay, the small clouds you see, very small, tiny. And they can be as large as thousands of kilometers. These stratus clouds or some of these cyclones, they are very big. Okay, they are all come under the same category. So when it comes to a definition of a cloud, cyclone is part of a cloud, the monsoon is a cloud, then the fog is also a form of cloud. They are all different types of clouds. And clouds are classified, they are given names just to help us identify what they are. Also many times when you report these different name of the cloud, you get an idea of, okay, this is the kind of cloud that is present in the sky. So that's the International Cloud Atlas. Okay. part of it is available on the net, not complete, and where they are given nomenclature to clouds, but what is the criteria used? It is based on the height, low level, mid level or high level, depending on the height. Basically, when you say height, it refers to the cloud base height. There are some clouds which are very tall. Even then, we go by the base height of the cloud, okay, where that base is located. Height could be very tall. So it is mid level or high level. Then it also refers to shape. Okay, like cumulus, like you see nice cauliflower looking clouds, they are cumulus. Then you have stratus, means widespread, like a blanket. Okay, we call them stratus clouds. Okay, so this you have very high clouds. Sometimes you find them during winter time. Nice, beautiful display in the sky. When I show those pictures, you will understand them better. So let me go to that and come back. Then we will see this. Basically, the nomenclature, the names are derived from Latin words like cirrus means curly, stratus means layer, cumulus means heap, nimbus means violent rain. Okay, this is connected to that. This is an example of cumulus clouds. You see, very small. But if you look at the width and the height, they are almost comparable, not much difference. Okay, individual blobs of clouds, we call them cumulus clouds. But there are varieties. Okay. The next variant of cumulus clouds is cumulonimbus. It is also has got this cauliflower blob shape, but the height is much larger. So, for example, if you look at the width, the height could be several times the width, and more importantly, they extend above the freezing level. This is very critical. If it extends above the freezing level, ice is present, then only we call it cumulonimbus. You may have tall cloud, but below the freezing level, we call it cumulus congestus. Cumulus congestus means the top is not above the freezing level, but it is below the freezing level. And often, they are one of the most violent clouds. They can reach as high as 20 kilometers. Okay? Penetrate the stratosphere also. That's how water vapor transport from the troposphere to the stratosphere takes place through these cumulonimbus clouds. Okay? If the cumulonimbus clouds are not very deep, then this stratosphere-troposphere exchange is limited. But through these cumulonimbus clouds, whatever you release at the ground, it goes all the way into the stratosphere, not just to, but into the stratosphere. Let me just go back. See, one of the things you see with the cumulonimbus cloud, sometimes you do get lightning. Okay, whenever you say lightning, it is the indication that both ice and liquid phases, they are coexisting. Only once that happens, you get lightning. Okay, in the absence of liquid and ice phase coexisting, you don't get lightning. But dynamically, that's not very important. It may be important for cloud microgravity, because when a particle is charged, it does change the way the interaction between individual particles takes place. And another important thing is that often you see outflow from this, which is shown more clearly. Okay. This is where the air from the surface rises in the deep clouds, because this is where maximum water vapor is from the ocean and from the evaporation from the surface that rises in the deep cumulonimbus clouds, and it spreads out at certain level. This could be as high as 12 to 15 or 16 kilometers, close to tropopause level. Okay, very deep. So transport of air from the surface to the upper troposphere takes place in these cumulonimbus clouds. Okay. After that, once it comes out, to some time it evaporates, it vanishes. But all those pollutants are left there, those things which are not condensed by the liquid and brought back to the surface. Okay, they are carried to some different places. All right. And this is the vertical extent. This height could be maybe a kilometer from the surface, and this is about 16 kilometers. So these are the only clouds which occupy the entire depth of the troposphere. Okay, they link surface with the left of the troposphere. In fact, when you see the tropopause, that is the interface between where the cumulonimbus clouds are penetrating and the stratosphere is. The interface is where you get this. Boring cloud, right? It's called stratus, which you sometimes find when the cyclone is there. No sun, okay. At the same time, no rain. Just all you find is widespread cloud cover. Okay? This is what we call as the stratus cloud. Stratocumulus, in the sense you are able to make out few isolated blobs, but it is not individuals, but they are connected and spread out. That's why you call it as stratocumulus. So if you look at this nomenclature, stratus means layer, cumulus means individual blocks. Sometimes you combine them to characterize in-between cases. Okay, similarly cumulonimbus. Cumulus means individual cloud, nimbus means raining. So when you have cumulonimbus means it is a raining cloud, that way. So you combine these. Are you familiar? Have you seen such clouds? When do they occur? Yeah. It's called altocumulus. It is a mid-level cloud, occurs around 5 to 6 kilometers height. Okay, you don't find them during monsoon or during after monsoon months. All right, mid-level clouds, and you see this nice structure. Alto is mid-level clouds. Okay, height is around 5 to 6 kilometers. Then evening sky, nice, beautiful, fibrous looking. In fact, all these are ice crystals. Okay, temperature is below minus 30, minus 40 degrees, very cold. So when it comes to cirrus, all the cirrus clouds, they are made up of ice particles, very high level clouds. Okay, there are examples of cirrus clouds. Sometimes when you have individual blobs, they are all ice clouds, but shapes are individual blobs, so you call it cirrocumulus. So let me now go back. Yeah. So you have stratus clouds, cirrostratus, cirrocumulus. These are all high clouds. You know what you see above 5, 8 or 10 kilometers above that level. You have low like stratus clouds, stratocumulus or nimbostratus. These sometimes if you have low level cloud but raining, you call it nimbostratus. You have mid level clouds, altostratus, you have seen that. Alto means refers to any mid level cloud, you call it alto plus something, altocumulus is there. And you have clouds with vertical development like cumulus and cumulonimbus you have seen. It crosses the entire troposphere. Okay. So these are the different types you saw. Just what gives shapes to these clouds? Sometimes you find this, sometimes you find this, another time you find this. Okay? What is the reason? Basically, clouds shape comes from the way the underlying air motion caused that cloud. Okay? For example, when you see this cumulus clouds or cumulonimbus clouds, actually it is the warm thermals from the surface they rise. Whenever you burst a cracker during Diwali, you see the smoke rising, right? It has got some similar shape. So if you have, this is what we call thermal. Thermal is nothing, a hot air which is rising, and whenever that occurs, then you get this kind of a shape. So the underlying mechanism here is nothing but surface air is rising in the form of these individual blobs of air and okay. On the other hand, when you have stratus, this occurs if you have kind of cyclone, approaching cyclone. Okay. Large area is undergoing slow vertical motion. Okay. Entire layer is getting lifted up. Then you get the stratus clouds. Sometimes decaying clouds also give rise to this. They merge together and form this cloud. So when you look at, similarly, when you look at this altocumulus clouds, which occur somewhere at 5 to 6 kilometers height, what happens is, this is more found during winter time. Normally, winter time, if you find, you have heard about these western disturbances, right? When they move, you have warm air here, cold air normally is at the bottom, warm air is rising, and somewhere, some distance away, you get this kind of clouds. Okay, it is an indication of more worse weather to come. Okay, so what happens is that cold air is always below, warm air is ascending over that. This is what we call slope convection. Away from the confluence zone, far away, you have high level clouds. That's where you find cirrus clouds. Cirrus clouds form sometimes away from these winter or cold air fronts, and also sometimes you get from the outflow from these cumulonimbus clouds. Both of them, they give rise to this. And this kind of a cloud, again, it could be approaching cold air front. That's possible. This one is again nearer to the cold air front. And gradually you see the cloud becoming thicker, becoming stratus, and finally it starts raining. Okay. So by looking at the shape of these clouds, you can make out what kind of vertical motions are occurring in the atmosphere, what's happening, what kind of weather to expect. Okay. It is like at a stethoscope. When you go to a doctor, sometimes they put like this and just check your health. Similarly, by looking at the shapes of the clouds, you can say that this is what is happening in the atmosphere. There is a stable atmosphere, unstable atmosphere. Do you expect bad weather in a few days, and so on. Okay, it's possible, but it's not 100%. So you can. It is a sign of approaching weather, but you can't be 100% sure. Okay, indication. So you have seen the different cloud types. And the question is how a cloud forms. Remember, by definition, cloud is a mixture. Condensed water is present. Okay. What it means, if the condensed water is there means liquid or ice and the vapor, they are coexisting. If that happens, it means there is equilibrium or saturation. Vapor is saturated. Okay. All the clouds, they are saturated cloud. Okay, saturated. The water vapor is saturated. Excess saturation is the one which has condensed out. So most of the time, somehow the air has to become saturated and ascend further. Only when it's super saturated, the excess amount of water over and above the saturation that condenses and gives rise to cloud. Okay. How does saturation occur? We can come to this cloud itself. Okay. Let's say we have air passing, let's say 50% related. Somehow it goes to this temperature, here it's saturated. This is the dew point. Right? Suppose you cool further, what happens? This is the vapor pressure, and this is the saturation vapor pressure. So if you cool to this level, then the actual vapor pressure is more than the saturated. Okay, that situation is not stable. So what happens is this excess vapor condenses such that the vapor pressure is on this line. So when you see a cloud forming, entire vapor will condense. It is over and above, which is this line, the saturation line, saturation value. That is the amount which condenses. So if the temperature at this level, only this much difference will condense. If you cool to this level, this much will condense. If you cool further, almost all the vapor will condense. Okay. So therefore, the condensed water is related to this element. Somehow liquid plus vapor still constant. You understand? It's only a question of changing from vapor to liquid or solid. But if you add up these two, the sum remains constant. Okay. So as the air cools, more and more vapor condenses and becomes the liquid or ice. Okay. In the atmosphere, most of the time, whenever it forms, it is related to this process. Air getting cooled and excess vapor is condensing out. Okay. The question is, what causes the cooling? One is vertical motion. You are all familiar, right? Whenever there's vertical motion, as you go up, the pressure decreases, expands. When something expands, it cools. Similarly, when something gets compressed, it gets hot. Have you ever experienced that? Something when you compress it getting warmer or hot? Okay. See, if you have bicycle, that pump, use it and see what happens at the bottom. You try to, just to experiment, you remove all the air from the cycle, then try to pump yourself, and when the cycle is full, you touch the bottom of your pump, then you see the hot. Where did that hot air come from? It's nothing but when you compress, almost like adiabatic compression, the temperature is increasing. Similarly, the reverse occurs when you expand. So when you expand, cools; when you compress it, temperature increases. So if you bring down the air, even if there is a cloud, it evaporates. On the other hand, if you lift moist air, okay, at some point it reaches saturation. That's what we call as cloud base. Cloud base is where you first reach saturation. Once you lift the air slightly above, it cools further, and this excess air starts condensing. So when you look at these clouds here, this is the point where the air first became saturated. Slightly below the level where you see. When you raise the level slightly above, excess water vapor condenses out. And as it rises further and further, here when you go to the top here, mostly, almost all the vapor is condensed. Somewhere here, hardly any vapor left. Okay. Everything is liquid or ice form. So after it comes out here, and the air which is coming out here is extremely dry. Okay. Almost everything is sucked out, everything comes back to the earth. Part of it has rainfall and re-evaporates, and moisture is part of the atmosphere here. But the air which comes out of these cumulonimbus clouds is outside this region is extremely dry, very dry. Okay. Although you see a lot of humidity, RH may be close to 100%, but the actual amount is so small that it practically devoid of any water vapor. Okay. It's very dry. That's what happens. Any questions you can ask? Can you?
Any relation between thickness or thickness of about the high clouds? Any relation with thickness?
Please repeat your question. Thickness of high cloud and?
There is high cloud means they are thick clouds.
Let me see. When I say high cloud, this is also high cloud. Okay, but it's here. In fact, it may look quite thin at this, but the actual thickness, if you measure bottom to top, maybe several kilometers. But the density of these particles is so small that you get from here, it looks as if it is very thin. But on the other hand, when you look at those cumulonimbus clouds, because you have so much water vapor at the surface, typically, if you measure in Bangalore now, there may be about 10 to 15 grams per kilogram or 1 meter cube of air. Okay. But when you go there, all of that is gone. So all of that is distributed in the column here. All right. So therefore, when you see these thick clouds, part of it condenses, part of it drains out. Remaining is still left. And this one. So you may ask this question many times. You see the cloud here.
What is 10 to 50 grams per meter square?
No, per meter cube, not meter square. See, yeah. See, what you do is, you can take a volume like this, okay? 1 meter cube, and say how much water is there. All right? That is, if you measure in Bangalore now, here it may be around 10, because winter it is very low. During rainy season, monsoon time, it goes as much as 15 to 20 grams per meter. Okay, what it means is, remember, 1 gram of water is also 1 ml. So if you take 1 meter cube of air and condense out everything, you get about 20 ml of water max. Very small. But this column of the air is so large that you get a lot of rain. And secondly, whatever the water condenses, everything doesn't fall as rain. Part of it still remains in the tiny cloud drops and later on it evaporates. It moistens that layer of the atmosphere. Okay. It doesn't fall down. Any question?
Is there a difference between summertime cloud and wintertime cloud? As there is no correction during winter.
Okay. See, as I said, shape of the cloud is related to the air motion which causes. Okay. Summertime, the forcing is you have strong ground heating, the thermals are rising, so it is more like convective clouds. So winter time, it is more like your mid-latitude systems where large-scale convergence is giving rise to them. Okay. At the confluence zone of warm air and cold air. These fronts, have you heard of? Cold front, warm front. So when the two meet, you get this slow ascending motion. Okay. So during winter time, you end up with this kind of cloud systems more. Stratus clouds or this. Summertime, more of convective clouds.
Is there a difference in size of droplets, cloud droplets, that form more ocean and that form more land?
Okay, I think I will come to that later part of my talk. Okay, there is a difference. So, how a cloud forms is that the ascent of the moisture, that's one way. Essentially, important thing is that air has to reach that saturation vapor pressure by cooling. That's one way. Okay. During winter, what happens is that you have heard of Delhi fog or Bangalore fog or all this fog sometime, right? Many places you find that. There, you have strong nocturnal cooling. In the process, daytime, you may be having temperature here or here, but nighttime, you have strong cooling, you cross this line. Just to do with the ground cooling. Okay? If that happens, you will get condensation. But the amount of water we get, condensed water is very small, not large. All water vapor got condensed, but still not there. But only when you have vertical motion or a long depth of the atmosphere, then you get maximum condensation. Otherwise, these are form a cloud. They are all clouds, but the condensed water amount is very small, not too high. Okay. So this experiment I already told in my last class. Okay, just it is not. I'm not going to repeat. But just to say one more thing, is that when you look at the droplet formation, okay, it is like trying to bring together naughty children in one room. Okay, each molecule is independent. They are moving at random here and there. But on the other hand, they are all chaotic. On the other hand, when a drop forms, it is more ordered. All right. So even when you take 1 ml of water, you know how many molecules are there? Water, 1 molecule, quite a large, 10 to the power 12, 22, 23, like that. Okay, in one. So even if a tiny drop, which is 1 micron size, the number of molecules you have to bring them together is very large. Okay. Remember that condensation and evaporation, they are dynamic processes. Okay. Suppose water condenses there. It's not sitting idle all the time. Part of it also evaporates back. Same thing happens in clouds. If a drop forms, all the molecules are not sitting there. They are also going back. Okay. So what you need is a friend who holds them together. Okay. Otherwise they are moving randomly, happy as they are. But if there is a friend or substance which allows them to come together and stay there for longer, that's how the drop forms. And we call them as cloud condensation nuclei. Okay. All the salt particles, they are very good cloud condensation nuclei. Sulfate, then sodium chloride, all these things. Okay. So therefore, you need a friend. That's what this form. And it is on these particles where your first condensation begins. Okay, salt particles, which forms the drops. So we call them as cloud condensation nuclei. If there were no CCM, sometimes we call the atmosphere is polluted, we have particles, okay? But as far as cloud is concerned, it needs some of them. If the atmosphere is devoid of all these cloud condensation nuclei, formation of cloud would have taken place, but not the way we see it in nature today. Okay? That would have been much, much harder than what it is today. Okay? Moment RH reaches 100%, any excess, it starts condensing out. That's how you get this. That's for the liquid, you need hygroscopic particles, like salt particles, sodium chloride or sulfate, like that. But when it comes to ice, they have different characteristics. You must have seen, if you stay in the hostel, no, it's easy to form friendship with some people and not with others. The reason is the wavelengths of frequency, they don't match. They talk at different, same thing in water also. Particles which are very good for forming liquid drop, they're very bad for the ice phase. Somehow they don't like ice. Okay. On the other hand, ice phase is crystalline. It has got some lattice structure. Okay. Only the substrates or particles which have similar crystalline structure, ice also deposits and forms very easily, ice phase. So many times what happens is, you have drop formed at one temperature, but even at minus 10 degrees centigrade, still remains in the liquid form. It is called supercooled liquid. Okay. Just because temperature decreased below 100, below 0 degrees centigrade, the freezing level, doesn't mean that it immediately becomes ice. No. It waits for the right opportunity. Okay. So therefore, in case you want to accelerate or form ice phase, it needs ice nucleation particles. All are not. Only some crystalline. Like for example, you might have heard silver iodide, cloud seeding material, one of the very popularly used. It has got a crystalline structure whose the lattice, the distance is same as that of ice. Then there is perfect matching. Otherwise, imagine that you have another crystalline structure whose these distances don't match. Then after few layers, they don't match at all and they don't stick that long at all. So therefore, when you see this ice phase forming, they need different kinds of particles, not the ones which are favorable for liquid phase. So ice nuclei are different from drop nuclei. Okay. These are all crystalline structures. So therefore, sodium chloride is very bad ice nuclei. Like mineral dust is a good. This one. Silver iodide is a good thing. That's why it is used for cloud seeding. The reason is this: they have to match at some location so that the energy is minimized. Let me go over this. Essentially, all these are concepts which take more. Let me come to the other question which occurs all the time, that many times we see cloud in the sky but it doesn't rain. It stays there for quite some time. What is the reason? It is related to what you call the size. Alright? When you see raindrops which are falling to the earth, 1 to 2 millimeters, sometimes even 5 or 6 millimeters, they're quite large. Their fall speed is of the order of few meters per second. Okay. On the other hand, when you go inside the cloud and weather, often inside that they are in the micron sized, few microns in size, most of the drops. Okay. And it is of the order of about 2 to 20 microns, that is the 1 to 20 microns. That is what we call cloud droplet. Once it becomes bigger, we call it drop. Actually, the cloud condensation look like the friends on which the cloud water molecules decide to form friendship, their size of the order of 0.2 to 1 micron, sometimes 2 microns. That's the range they are. Okay. So therefore, these are so tiny that their fall velocities are of the order of millimeters per second. Okay. If it's so tiny that the fall speed is so small, it will not reach the surface at all. They still remain suspended because you have little turbulence, vertical air motion taking place, which is the order of meter per second. When you have turbulence of the order of meter per second, And if you have this fall velocities of the order of millimeter or centimeter per second, they will not come out of the cloud at all. They remain suspended. They are carried with this one. So when you see fog during winter, that's what happens. That they are so tiny that they are not big enough to fall rapidly to the surface. There is a small fall velocity, but that is not strong enough to separate from the cloud and fall to the ground. Only when it grows to bigger size, then the drag force is so large that it's able to, so not the drag force, gravitational force is so large that it's able to come out of the cloud. Okay, so cloud is there, but no rain is related to the fact that drops are not reached to the big enough size. Okay. So if you try to compare them, put them together and see how big the changes are, what changes are there. On a relative scale, this is how the cloud condensation nuclei is. Then when a drop forms, relative to that, it looks so big, bully. But the actual drop is real bully, very big ones. And there are various processes which takes place within the cloud, which is related to condensation, collision and coalescence, which dominates the warm clouds and ice crystals, which is called cold clouds. All these are important, okay? But I'm not going to go into the details because that itself is a over a 2 hour long lecture. But what you remember is that within the cloud, all these are present simultaneously. Only the ones which have reached big enough, then they fall to the ground because of the gravitational acceleration. So what is keeping these small things inside is the drag of the air. You are all familiar with the fall velocity, right? Gravity versus drag of the air. As long as the fall velocity is less than a meter per second, they don't come out. They still remain in the cloud. That's what you see as a cloud. And so it is related to size of the drop inside. And inside, if you see, below the freezing level, almost all, it is all water in the liquid form. Between freezing level and up to about minus 30, minus 40 degrees, we call mixed place, because sometimes both cold water, we call it super cold, and ice, they coexist. But once the temperature is below minus 40, no liquid is there. Okay, below minus 40, only ice phase is present. Okay, between 0 and 40, it could be ice, liquid, because liquid can be in the super cooled form when there are no ice forming particles. Okay. On the other hand, if it is below minus 40, immediately it freezes, it becomes ice. Okay. How does the droplet really grow? It is a very long trajectory. Remember, condensation forms somewhere here, about meter per second, that's what the ascent is. But within the cloud, as it moves, more and more vapor condenses, and also it collides with some other particles. So collides, some of them merge, some of them not, but it is this continuous process. So as it rises in the cloud, it is here it's maybe 1 kilometer, it could be 5 kilometers, 10 or 15 depending on the height of this cloud. So therefore the distance it travels is quite long. It is not short distance at all. So along this long distance, collides with others and starts growing. Few of them, so not all of them. And once the size reaches such that its fall velocity reaches about 2 to 3 meters per second, it no longer is there, it starts the downward journey. As it falls, it collects more and more smaller ones along the path. So the size is maximum when it just leaves the cloud base. Okay, it's a very long trajectory. It could be 5 kilometers, 10 kilometers, 20 kilometers, or 30 kilometers, depending on the turbulence level here and the depth of the cloud. Okay, so it is this process of collision, coalescence, and change to ice phase. All these are involved. And whatever you see at the ground is a final result of whatever the complex processes which take place inside a cloud. And importantly, this entire thing takes place on a short time scale of 20 days. Okay, that's important. Given a lot of time, things could have happened. But in nature, this entire process of starting from condensation to fall of rainfall is about half an hour. Okay? In about 1 hour, the cloud dissipates and a new cloud forms. Within that, the rain has to occur. So it's very rapid. In fact, it is quite amazing that if you see the change in the mass of this to this, okay, it's a million times. A tiny droplet becomes a drop and falls to the ground. Change in mass of that is a million times. So now you can compare that with your growth. When you are born, few kgs, adult 50 to 100, what is the change? Maybe 20. And occurred over 15, 20 years. But here, in about 20 minutes, imagine you are increasing the mass by a million times. Okay? That's why it's so complex. But it does occur. So these are all normally in nature, especially cloud, it works on inequality. If everything is equal, you won't have got rain at the ground at all. Unequal, what happens is one is bigger than the other. So size does matter. So normally this one moves slower compared to the smaller drops. So there is relative motion. When there is relative motion, some of them they collide and it collects. Few of them, not all. Okay, few it collects and becomes bigger. Once it becomes bigger, section increases. It is able to, the relative velocity difference also increases. Okay, able to collect more of them along the path. So as this big drop traverses through the depth of the cloud along its path, it comes down, it is able to grow very rapidly. By this process is called collision coalescence process. Okay. So essentially, if all were equal, the relative velocity would have been same. It means they all move at the same velocity. Relative velocity is very small. Okay, hardly any relative velocity. The chance of colliding is reduced. So therefore, the droplet growth is not there. On the other hand, if there is one big drop and others are tiny, then they move faster. This moves, means they may be moving upward or this, but there is a large relative velocity. It is this difference which is causing them to collide with each other and grow in the process. So in the cloud, inequality is necessary. Some have to be big, some have to be small, and it is this way. And the minimum size needed for collision and coalescence efficient to be this thing is about 20 microns. If they are smaller than this, they come nearer, collide, but the surface tension is so strong, they don't merge. So to overcome that surface tension effect, it has to be bigger than 20 micron. So critical thing is to reach about size of about 20 micron. Once that is there, then it is different. But on the other hand, if the temperature is below 0 degrees centigrade, and if you have ice crystal, the mechanism is totally different. Okay. Here we call it a Bergeron process, where in fact, when ice particles are present, that is below 0, when the cloud top is above the freezing level, and even if there is one tiny ice particle present, it will change this droplet formation also, precipitation formation drastically. So you have to distinguish two processes. One is cloud formation, which is related to reaching saturation. But precipitation formation is very different. Okay, that occurs provided something inside the cloud encourages the formation of bigger sized drops or ice particles. Okay. So many times you see a cloud but no rain. It is related to too many small particles, very few big ones. So earlier there was a question about marine versus land, right? Basically over land you have too many of these tiny droplets. So small because, for example, a given amount of water is distributed among 1,000 or 5,000 individual droplets. On the other hand, same thing is distributed among 50 or 100. The size is quite different in the two cases. So when there are too many tiny of them, they like to maintain their identity. Collision and coalescence is not favored. In the process, what happens is that they don't rain at all. On the other hand, if there are few big ones like salt particles are present, they tend to grow at the expense of smaller ones. So the nature of the CCR, how many numbers are there, their chemical composition, all matter when rain is there. So ocean and land CCR, that is. Okay, that's where this rain mechanism could be quite this thing. Over land, in fact, this is more preferred mode. Because when ice particle is there, the mechanism is totally different. You don't need that thing. Now coming to the climate. Okay. One effect is the way they release the heat in the atmosphere. When the condensation begins, what the water does is that it takes away heat from the surface because part of the energy goes in evaporation, that goes and condenses out in the atmosphere. So you are essentially transporting energy from the surface to the mid or upper atmosphere. That is one mechanism, okay, which goes towards driving the large-scale circulation and maintaining the wind system. That's one effect. It is also important for the climate. The other important role in the climate is by interfering with solar radiation. Like for example, if there is no cloud at all the radiation from the sun, of course it gets absorbed by the aerosols and air molecules. Rest of it comes to the surface. Any idea how much, suppose 100 units of radiation come here, clear sky conditions, what fraction of this comes to the surface? At the top of the atmosphere, you say 100 units. Clear sky conditions, let's say no aerosols, only the absorption by water molecules. How much of that you receive at the surface? You understood the question? Okay. At the top, you have 100 units. Clear sky, no aerosols, how much is the energy received? How much? Yeah, it is about 80 to 85%. Okay, about 10 to 15, about 15% is atmospheric absorption, molecular scattering as well as absorption, both are. Because shorter molecules they get, shorter wavelengths they get reflected back also, molecular scattering. But when it comes to cloud, that could be much larger. It could be 100% almost. Because when you see these thick, dark clouds, top of the atmosphere still sun is shining, but at the bottom, almost no radiation reaching. In fact, at the top you may get around more than 1000, about 1300 watts per meter square during daytime, top of the atmosphere. What comes at the surface, clear sky conditions, maybe about 1100 watts per meter square. But when clouds are there, thick clouds, what they do? They do two things. One is scatter. That's why when you see that satellite imagery, wherever you have these clouds, they appear white because more solar radiation is scattered back. Okay, that's what we call albedo. It could range from 20 to 80 or 90% depending on the type of the cloud and how many number of water drops are there. Okay, one is albedo effect. It simply reflects back. It also absorbs radiation. Part of all the short wave also not simply reflected back, part of it also absorbed. Okay, and so therefore both short wave also gets scattered back and also absorbed. That's one effect. The other one is the way it interferes with the emitted radiation from the Earth's surface. When you have a cloud here, the radiation which is emitted from the surface, it is absorbed there. Okay, and part of it is also emitted back. Because it's almost like a black body. Little is reflected, but essentially emitted back. So, in the process, the cooling rate of the surface is reduced. So, you might have seen that when the largest cooling takes place, when the sky is clear. Okay, whenever you see a clear sky day during winter time, then you expect lowest temperature at the ground. On the other hand, if you find a cloud which is there at some level, on those days, the surface cooling is reduced. The reason is it is not letting the long wave radiation to escape to sky completely. Part of it is absorbed and then emitted back by the clouds. Okay. All right. So it is. So therefore, when it comes to the radiation effects or climate effect of clouds, directly it interferes with the solar radiation. So it contributes to the mean albedo of the Earth. Okay. For example, if I go back, here, okay, the oceans look very dark. Do you know the albedo of the seawater? About 5%. What it means is that 95% of the solar radiation is absorbed. Only 5% is reflected back. That's why whenever you see this under clear sky conditions, if you see oceans, they all appear black. Okay. Land, on the other hand, higher reflectivity. Depending on the vegetation or the sand, it could vary from 15 to 25 or 30%. Okay. But the brightest objects are these clouds, what you see. Okay. That is. Yeah. Yeah, they basically interfere with solar radiation. So they contribute to wind albedo because they appear bright, so the average albedo of the Earth increases. So they can change the effective emission temperature in the atmosphere. How? Because if you have cloud present here, what it does is that it doesn't let the radiation coming from the surface to escape to sky, but it absorbs and it emits at the temperature here. But on the other hand, if the radiation from the Earth were allowed to escape directly, you have warmer temperature emission. Okay. So therefore, whenever you have clouds, they appear as dark spots in your satellite imageries. Cloud temperatures are colder than the emissions from the surface. So this is what happens. They can change the effective emission temperature in the atmosphere. So it is related to infrared or terrestrial radiation. And they absorb the radiation emitted by the surface and re-radiate it. Okay, they radiate back. So these are the processes by which, but the actual contribution, it depends on, like for example, directly interfere with the solar radiation. If you find cirrus kind of a cloud, they let in more radiation come, but they reduce the radiation going out. So it is a question of what kind of a cloud, what is the altitude, what is the composition, all that matter. Just to give you a flavor of how clouds interfere with the Earth. What is shown here is, yes? Any question? So what is shown here, the solar radiation measured at the surface, 24 to some days, starting from July 1st. Like for example, you see all these spikes here. On some day, it is less. Another day, almost you don't see any spike at all. Okay, this is nearly a clear sky day, but if you see this day, here it's much more. Okay, on this day, high-level stratus kind of clouds were there. Means they are not completely opaque, transparent, but not completely transparent. They reduce the average radiation coming to the Earth, that's why peak is less. But you don't see these spikes. On the other hand, whenever you have these passing clouds, cumulus clouds, a patch is there, it reduces the radiation, it gets over, again the radiation goes up. So when you see measure radiation, if you notice these spikes or this increases and decrease, rapid increase and decrease, it is an indication of presence of cumulus clouds. Okay. Now, this is the net long wave radiation, the difference between what's coming in and what's going out. Okay. Normally, our ocean in a clear sky day is about 50 watts per meter square. Okay. But whenever you have these clouds present, it reduces. It comes down to as low as 20 or 10 watts per meter square. You remember on this day, this has reduced substantially. Okay, it has to do with absorption of the radiation and re-emission. Okay, because that emission temperature. So therefore, you can see that the largest one is shortwave attenuation. The other one is it reduces the long wave loss, cooling in long wave. Okay, so these are the two effects which clouds have. So by reflecting solar radiation back to space, this is called the albedo effect. And by trapping infrared radiation emitted by the surface and the lower troposphere, it's called the greenhouse effect. Okay, one is albedo effect, it is directly radiating back to this one. The other one is greenhouse effect. Clouds exert two competing effects on Earth's radiation budget. These two effects are usually referred to as short wave and long wave components of the cloud radiative forcing. Okay, it has got and the balance between these two components depends on many factors, including microphysical. When you say microphysical, the droplet size, how many numbers are there, how they are distributed in this thing. And one is microphysical is that, macrophysical is the shape and size and those things. And cloud properties. Okay, in the current climate, cloud exerts a cooling effect on the climate in the global mean. If you take the average over the globe, clouds on the whole have cooling effect. But locally, the effect could be warming or cooling depending on so many factors. So, what happens if clouds are there? They have other influences which are not included in the previous. One is that they are source of water on land. Like you have seen the difference between desert and a tropical forest. Right? There are a lot of difference, even in their radiation characteristics. So, clouds play an important role in the hydrology on the vegetation. When the vegetation changes, the way the amount of radiation absorbed and emitted also changes. So, that is another effect of these clouds. Okay? By precipitation fall. This is not the direct effect, it is the indirect effect, because once the precipitation is there, vegetation is different, that changes the hydrological cycle as well as the radiation budget there. That's the other effect. Control the soil moisture and vegetation. When you have soil moisture change, the emission also changes. Okay? Even for dry soil. And other influence of clouds is the redistribution of moisture in the vertical. Where does it go? You know the largest greenhouse gas in the atmosphere, which is the water vapor, right? So what the clouds do is they redistribute the water vapor in the vertical. Okay, thereby redistributing the greenhouse gas vertical. All right. So therefore, redistribution of the moisture in the vertical, the vapor itself has an influence on the radiation budget. And it also washes out the aerosols. Like many times if you see before the rain, the sky is kind of opaque, not very transparent or clear. But after the rain, it looks very beautiful blue sky. It has to do with washing out of the aerosols. So these are the effects which are not the direct effect of interfering with radiation, but indirect effects. Okay? But when you look at climate, all these are important because they contribute. Like when you look at that IPCC reports, 1 watt per meter square, half a watt per meter square, those are the uncertainties. But each of them are in the same range or larger. Okay? So therefore, these are all indirect effects, but important to the climate. So what happens if there is warming? So in response to global warming, the cooling effect of clouds on climate might be enhanced or weakened, thereby producing a radioactive feedback to climate. So therefore, it's not clear we're going to enhance or this thing. So a lot depends on how people argue about it. Okay, and who argues. Whoever has more clout, they win. You know, whenever the uncertainty is large, the scientist who has higher weightage, they're saying gains more weightage. So when it comes to climate science, truth is defined. Remember that. In science, you find out the truth. But sometimes you define the truth. There is a difference between the two. The one, when you find out the truth, it can't be changed with people when they change. On the other hand, when you define a truth, it changes as the person is gone. Okay. In climate science, especially when it comes to the effect of clouds on climate, in fact, you define, okay, this is what is, you define a scenario saying these are the sequences, and you say that, okay, this is what happens. Earth is going to cool or going to warm, depending on how we argue about it. Okay. But final word is not said. Lot of scope for research. So especially if some of young people are looking for research topic, one of the very fertile areas. Okay. So when you want to look at the climatic effect of clouds, there are various linked influences. Okay. What are those? Like for example, something called boundary layer clouds or low level clouds. They are the clouds you often see, okay, shallow clouds. Then you have these deep convective clouds, the ones I showed you, the cumulonimbus which penetrate all the clouds. Then you have these annual clouds which form as outflow from these cumulonimbus clouds. Then you have cirrus clouds you have seen. Then also you have mid-level clouds, all these. And the response of the climate depends on the response of these types to the global warming. All of them, they don't behave the same way. Some of them increase, some of them they decrease. And finally, it's the combined effect of this. When you look at the sky here, all of them are present somewhere or the other. It is not that one is present, only other is not absent. All of them are there, sometimes in the same place. Because when the deep cloud is there, you also have shallow clouds. You also have mid-level clouds. But in some places, only shallow is there at some time. Okay. So, in the perceived, how you model the effect of this is what matters to the climate. And that is an open question. But that's where I said, defining the truth becomes important. Okay, I define this way and I get this influence. I define this way, I get another result. So, it's a question of how you argue, you end up with different results. So, one of the arguments in the global warming scenario is this, that if the surface is warmer, then you have more energy at the surface, so it's more water vapor. The temperature is more means it can hold more water vapor, so it increases. So you will be able to form much more intense clouds here, because more water is there, more energy available, so your clouds will be much more oily. Okay. So therefore, if the clouds are more intense, they form these narrow, intense convective systems. So there is either, therefore you expect the short term but more intense rainfall events. Okay. And if you look at data from the last 10-15 years, there is some suggestion of this, that cloud durations are reducing but intensity is increasing. Okay, that's one of the climatic effects on the cloud, not in the other way around. But the least studied clouds so far, in fact, if you look at all the clouds, normally the most focused is the cumulonimbus clouds, which provide rain, important in the climate because they are the ones which are responsible for circulation. Like for example, the tropical circulation, if you see, tropical circulation is driven by the cumulonimbus clouds. Then another set of clouds which occur more frequently, they are called boundary layer or shallow clouds. Okay. So far, there is no detailed study on them at all. There is another open area where you can take up about how much they contribute to the climate. What happens with the climate warming? With the ground cover of these boundary layer clouds, they increases or decreases. They don't have much dynamical effect, but they have strong radiative effect because they are very good albedo, they scatter radiation, so they have cooling effect on the surface. Okay, but this effect has not been studied in detail at all. In fact, most of the studies are limited to cirrus clouds and cumulonimbus cloud systems. Okay, but when it comes to boundary layer clouds, which actually occupy larger fraction of the surface area, there are less number of studies. In fact, large regions are covered with what we call as boundary layer clouds. They are there in the regions where you don't have this deep convection. and they play a major role in the climate because of their interaction with the radiative processes. Understanding their physical and associated radiative processes and their representation in numerical models is a major task, because present even climate models, not much attention is given to this radiative. Only now people have started thinking about we should include them, but not many studies are there looking at observations like this. So some argue that global climate warming increases the boundary layer cover, it increases albedo, therefore it is a negative feedback. Okay, see this negative feedback, because if it increases low level clouds, it is going to increase cloud cover, it is going to reduce the radiation reaching the surface, and therefore negative feedback. Some models do not predict increased cloud cover at all. Okay, in fact, cloud optical depth decreases. Then it reflects back less shortwave radiation. Okay, therefore, the shortwave cloud radiative forcing is reduced now, because that's the other way of arguing it. So it's going to increase the warming. So depending on how you model these shallow clouds in the model, how you distribute that water and into droplets. In the mid latitudes, models indicate decrease in overall storm frequency, but increase in intensity. This is in the related to mid latitudes. And poleward shift in the storm tracks. These are the things which you expect with the global warming in there. I think, let me just. Indirect anthropogenic effect. Okay, I think perhaps Professor Satish Kailas, not this one, SK Satish, may also talk about aerosols and clouds, a little bit of it. One of the increased influence of anthropogenic activities is that the amount of aerosols in the atmosphere is going up. Deforestation or change in this thing, release like thermal power stations or burning of fuels, all these things, increasing these particles. What they do is that this is a case where you have unpolluted cloud. But if you have a large number of these pollutants, what happens is that same amount of water is distributed among more number of particles, average size decreases, that collision and coalescence efficiency is reduced. The net result is that the life cycle or life duration of these clouds increase, because if it rains quickly, it dissipates fast. But on the other hand, more number of tiny drops or droplets, they stay in the air for longer, they interfere with the radiation for longer. So therefore, they change the radiation balance of the Earth. So that is the other. It rains less, but radiatively it is causing the cooling. Okay, this is the influence of anthropogenic influence. All these are taken from IPCC Air 4 report. Okay, whatever I have said on these climate effects. There are also some argue that it increases the rainfall. Looks counterintuitive, right? You think that once you have more number of CCM reduces the average size, so you expect the rainfall to decrease. But there are also people now who argue that it is going to increase the rainfall. So how does that argument work? You have to find a path for that. The way it works is that you have warm rain process in which collision and coalescence dominate. That is occurring if you have natural aerosols or more number of particles. But when you have more number of aerosols, it prevents this case. Shallow clouds, they don't rain at all. But on the other hand, if they have a chance to go beyond the freezing level, because many of these anthropogenic aerosols, they are very good ice nucleation particles. So here, ice physics becomes very active. Okay, in the process, whatever the condensed water is there, it has not rained out. It is rained within the cloud, and now that becomes ice. What happens? Once ice is there, it again latent heat of freezing is given out. As a result, the cloud is now able to grow very rapidly in the vertical. So once ice physics becomes active, rain process is enhanced. So therefore, what they expect is, in the presence of this polluted atmosphere, the warm rain to reduce, but on the other hand, clouds to become deeper, and because it is deeper, it also is more intense. Intense rainfall events to increase, and as a result, it can also enhance your overall amount of precipitation, because if the cloud depth is this much, you have less rain. On the other hand, you have much deeper, taller cloud, it also enhances your overall precipitation efficiency. See, now it's a question of how you argue. Okay. On one hand, you argue that more number of small drops, it decreases the collision efficiency, the decrease in rainfall. On the other hand, you say that because the rainfall has decreased, ice physics is not operating, so more water is retained within the cloud. So when that becomes ice, it is going to enhance the cloud activity and lead to increased precipitation. So both these arguments are going on. Okay. So there are very strong lobbies for both. Okay. It's not that one is dominating us. So you see papers in Nature appearing on this topic. Okay. Someone saying going to decrease, the other one saying going to increase. There are nice science and nature papers, arguments are going on. If you want to join, you can join that, but you should have a very clear idea and a mechanism to explain that this is the way, these are the links, this is the mechanism works. For this reason, I expect this. Okay, it should be some connection. So then you can argue and arrive at a conclusion. Okay, but this is a hot topic now. Okay, I stop here and open the floor for any questions if you have. You know, in these cloud models, they come with odd amount of complexity. Okay. So depending on which scheme you use, okay, one is cloud parameterization. Other than that, there is cloud microphysics. It is in microphysics they involve all this. Supercooled water, then there's ice, then the grapple and all the needle, different shapes, what temperature it takes, effect, all those complexities. So if you see some of these schemes now, they're extremely complex.
Supercooled water will be function of CCM.
See, supercooled water is not just a function of CCl. It is also a function of ice nuclei. One, what kind of chemical composition of that, its size, and also the temperature. Okay. So this is one. There is one difference between cloud condensation nuclei. When you say CCl, cloud condensation nuclei, it is between liquid and vapor. Vapor is forming a liquid drop or droplet. Is called CCl, that particle. On the other hand, ice nuclei is where directly vapor deposits into ice. This one. Okay. It turns out that the physics of this ice nuclei is very complex. A given dust particle or particle may not be an ice nuclei at minus 10 degrees centigrade. But the same thing you cool to minus 20, it starts acting like an ice nuclei. Okay. So it is related to the chemical, the nature and the crystalline structure. So ultimately everything is boiled down to something called surface energy. Okay, which relates to surface tension and contact angle and all those details, but that is too complicated. But what happens is that when it comes to ice phase, a nuclei or substrate need not be ice nuclei at minus 5 or minus 10, but same thing acts like ice nuclei at minus 15 or minus 20. It's a strong function of temperature. Then you have to know its chemical composition, what it is. So therefore, when it comes to that CCl, relatively simple problem. You know the size, you know the chemical, you know this is the supersaturation, it becomes liquid drop. But on the other hand, same ice nuclei is a lot more complicated. Okay.
What would be the fraction of this?
There are no measurements. Okay. Everything is a guesswork. Okay. Now, if guesswork is involved, how do you arrive at your solution? Okay. What you do is you change this, you change this, you say, then you say which one gives better agreement with the observations. All right, you keep that. You try different combinations. Okay, there are, when you look at these cloud microphysics parameterizations, you prescribe various equations, but there are coefficients are there which look very arbitrary. Okay, you make it 0.1, you make it 0.2 and see when the good agreement is there. Okay, you fix this is a good value that way. Okay. So it is more of an art than actual science. Yeah. Other questions? Yes? Solar. This one? Yeah. This is the shortwave radiation. Incoming. Downward, yeah.
So your peak is there at 25, that is 0 or 12?
This is a midnight. Okay, this is, yeah. So it is, this is midnight to next midnight, one day. So during daytime you have this. See, the difference between long wave and short wave is that for short wave it is a strong diurnal cycle. It is there during daytime, night, there is nothing. But when it comes to this long wave, it is there 24 hours. Okay, so there is a difference in the nature. This acts 24 hours incoming. Of course, if you are in the tropics, it's about 12 hours. If you go to high latitudes during some part of the year, you may have 24-hour radiation. Okay, but then during winter, it's just the opposite. 24 hours, you don't have any radiation. So therefore, solar radiation has a very strong diurnal cycle. On the other hand, long wave radiation, it is more function of a synoptic conditions rather than strong diurnal cycle. Okay, acts 24 hours. Okay, small question. We all talk about long wave radiation. Any idea how much radiation comes from the sky to the ground? Not in the solar radiation, but in that long wave radiation. Right? Understood the question? You know, all of us emit radiation, right? Even the sky emits. So therefore, when you see the Earth's surface, from the sky, some amount of long wave radiation is received. Yeah, this one. Even in the absence of clouds, you have some amount of long wave radiation coming to the Earth. Okay? Suppose there is no cloud at all. How much long wave radiation comes here? When the cloud is there, of course, it is changed. 10 watts, 50 watts, 100 watts. Same as? How much is OLR? 340. Okay, but here it is larger. Because part of the OLR which is outgoing radiation emitted is absorbed here by CO2 and water. So what goes out finally even under clear sky conditions is like 300 watts per meter square. But coming from sky towards this one is much larger. Actually, in warm temperatures like we are here, it is of the order of 400 to 500 watts per meter square. It acts 24 hours a day. Solar radiation, you average over 24 hours, what is the value? Daily average solar radiation. Yeah, 340 at the top, but actual surface is of the order of 300 watts per meter. That's the maximum solar radiation you have. So when you look at the quantity wise, individual component of this long wave is larger, but we are also emitting back in the long wave. Okay, so the what you call net long wave is of that about 20 to 100 watts per meter square. Like when you don't have most water vapor, less is received. Okay, then you get larger net long wave. Otherwise, you are emitting, something is coming, the difference is small, about 50 watts per meter square. But individual component of long wave is larger than the solar radiation. Okay. Any other questions? No, all clouds, top also, they absorb. No. See, water vapor absorbs in certain bands, not everywhere. Okay. In fact, the solar spectrum we see at the surface, it is already after absorption by water vapor, carbon dioxide and oxygen and everything. Okay, but the absorption is by within the cloud. What happens is water also absorbs. Okay, water also absorbs shortwave radiation. Okay. So therefore, when when radiation falls on a cloud droplet, part of it is absorbed, part of it is scattered. Okay, part of the scattered goes and falls on another drop. It gets partially absorbed and again gets scattered. So the multiple scattering is involved. So when you have a deep cloud, okay, a large amount of shortwave is still absorbed. Okay, and part of it is scattered. Okay, it is a combination of these two. It leads to that dark cloud. So many times when you see the cloud base, and it looks dark, what is the reason? Because not much radiation is coming from that cloud base to your eye. That's why it appears dark. Okay then, we break for. So after lunch, 2 o'clock, you come back, and just to give you a feel for what these measurements are, I'm going to give you the psychrometers. All right? You take measurements within the room, outside, top of the building, bottom, some 4 or 5 values, just to you can get a feel for what the numbers are like. All right, how to make measurements. So that is after 2 o'clock we reassemble in this. Was it better now?